Hello everyone and welcome back to this next lecture. So in the previous lecture, we had verified the working of the PLL when even if there is an integration offset. So we found that now by including the low pass filter into the PLL algorithm, we've been able to generate a smooth waveform for the frequency signal, right? And this smooth waveform was comparable or even better than the waveform that we got when we had no integration offset in our integration, or rather when we integrated we got no integration offset because we chose the grid voltage to be a pure cosine waveform. So now we'll go to the next level and change the grid frequency. So the way we are going to do this is, let us open the circuit file for this system. So we are going to change our voltage source from being a simple voltage source to a control voltage source so that we can vary the frequency as and how we need it. So all we have to do is change this voltage source to a controlled voltage source. Right? Save the file. Let's go back here to the main page. Since we made a topological change, we need to process our circuit schematics. We don't expect any errors because all we did was change a particular voltage source. So we just need to go to edit circuit parameters and check out this new voltage source that we got. So it's a controlled voltage source, right? All we need to do, we don't really need to change much because of the component position as 80, the polarity is at 70, which is the same as before. So nothing has really changed. Let's just give it a voltage name, right? So we'll just go here and call this grid voltage. This is just more for internal debugging purposes. So with this, we're good to go. Now we can go back to our control page and we can add the grid simulator file that we had created before. So for example, if we go to our peak calculation, we had created a grid file that is grid simulator. So let us copy this file. So I would go to my file browser, go to the peak calculation and pick out this grid simulator and the descriptor file. So let's just select these two, copy it and bring it over to the PLL case. So here let me paste it. So I'm going to add these two files in my simulation. So let's go over here, make sure you're in the right directory always, and pick out the grid simulator.py file. And we'll call this grid simulator. Save it. And let us just quickly go and upload the descriptor file so that we have a basic grid simulator working. We can then change it as we need to, right? So let's go over and check out what this grid simulator is. So this grid simulator up till now, all we had done was we were changing the magnitude. Right? The only thing we're going to do different is we're going to now change the frequency. So everything remains the same. Nothing really needs to be done because all that it does is it hooks up the grid voltage that you're producing with the output. That is, the control voltage source is the output target. Right? Nothing else changes. We don't need anything else. So it's a pretty simple control file. So nothing to be changed here. The only thing we're going to change here is instead of changing the magnitude, we are going to change the frequency. So for these times, and what I would do, I would extend this a little. So let's say, for example, I would make this between 0.5 and 0.7, right? So just extending the simulation is a little, and the reason is because of how our simulation works. So for example, if you take a look at this, you see that it takes around 0.3 seconds to settle. All right. So there is no point in introducing an event even before that because the PLL has not settled to begin with. It's only advisable that the PLL should settle. Now you might think this is a problem, but in reality almost every system needs some initial time to set up, or rather to start up. So a few, even this is like less than a second. It's like we're talking about a fraction of a second. A fraction of a second of startup time is quite acceptable, except if you're looking at high performance systems. Alright, so I would put my event at 0.4 instead. right? Just to be on the safe side and so that we gain time in terms of simulation. So I'll make this 0.4 and 0.6. So between these two times, let's drop the frequency to 49 Hertz. And for the rest of the time, let's keep it at 50 Hertz. Right? So you can actually increase it also to some other value. That's also possible. So let's do that. Actually, we can increase it to 51 Hertz. So the frequency, actually, this doesn't really matter because we have this if else block, which means between these time zones, it is 49, otherwise it is 51. So this initialization is actually useless, but it doesn't really matter. So with this, we will get a grid voltage. So let's go over, I'll just close this. Let's go back and run this simulation. So as always, go to the command line, make sure there is no error, and now we are good to go. So this simulation may take some time. So what I'm going to do is I'm going to pause this video and come back when it's done. So the simulation has been now running for a while and we can now check out the results. So let me go to the web browser and let's just check out the grid voltage, right? So you see the grid voltage has now been running, right? So we still have not reached the stage where the event should have taken place. So we still will have to wait a little more. That's okay. Now there's only one thing which I would say, one change which we might want to make, and that is with respect to our integration. So this integration would probably need to happen where we've multiplied it by omega rated. We should probably change it to omega PLL, right? Because eventually we do want this to be multiplied, or rather when the integration should take into account the actual frequency of the grid and not just the rated frequency. So this is a minor error which we can check. However, as I said, since the frequency changes by only 1%, we are not looking at a huge error due to multiplying it by omega rated. So this is totally up to you, right? This is totally up to you. I will leave it as it is, but as a suggestion, you can change this variable from being omega rated to omega PLL. So this way you're multiplying the integration by the actual frequency that you've estimated and not just a rated frequency. So anyway, let's go back and plot the frequency. And here you see the result. So the results are very interesting. As you can see, we now have the startup which grows gradually. So for example, this is 51 Hertz, and if you notice here, we are now at a frequency this is omega radian per second. So therefore this is now more than 320, right? If you just take a look, this is around 320, and this is expected because the frequency of the grid is now 51 Hertz. If you make sure, if you go back here and have a look, the grid simulator, even though I'm initializing here at 50 Hertz, because of this else block, the frequency is either 49 Hertz or 51 Hertz. It is under normal circumstances 51 Hertz, and only between these time period is it 49 Hertz. So therefore, if you have a look at this, it is expected that initially the PLL locks onto a frequency corresponding to 51 Hertz. When the event takes place, so the event takes place around 0.4 to 0.6, between this there is a transient because the PLL needs, or rather requires, some amount of time to lock onto the new frequency. But if you look, within just 0.1 second, the PLL has picked up the new frequency and it seems to have locked on here, right? Now, let's, as I said, always verify your control using several variables. Do not just pick on one variable. So let's plot on this trigger voltage as well. This is the voltage of the trigonometric expression that we are trying to force to 0. So let's go and have a look at what that is doing. So it should be, what's the name of the file again? I forgot. The name of the file is PLL trigger. So let's go have a look. It is this voltage, PLL trigger. And here you see. So, Initially there's some amount of transient, and finally when it is about to settle, you see that the trigger voltage is close to 0. So that means here the controller has begun to settle. Alright, it has settled to a steady state, and at this time we also see that the frequency has also settled to a steady state. When the event takes place, it does seem to affect it. Now, if you do notice, even though our frequency seems to have settled, the trigger voltage has not yet come to that. Trigger voltage still needs a little more time, right? So really speaking, a trigger voltage will only settle in 0.3 or maybe more, right? Now, the question again here is it something that you want to settle? Is this something that you want to correct, or is it something that you're okay with? Because remember, 0.2 seconds corresponds to around 10 cycles, right? So which means when there is an event, and this is a jump in frequency. So remember, it's very important to understand that in a power system, frequency will rarely ever jump. A frequency will start drifting. So really speaking, this jump that we have implemented is very rarely going to take place. A jump like this means there is a serious event in the system. Like for example, a generation has gone out, or a transmission line is blown off. Something like that, which has caused a huge impact in the system. That is usually what happens when you have such a huge frequency jump. Typically, when there is a case of load increasing, for example, as during the day the load keeps on increasing, let's say in a summer month as everyone is turning on their air conditioners, the load keeps increasing, the frequency will gradually decrease. So you won't see such a drastic jump, you'll see a gradual drop. And therefore, we do expect in such cases that the frequency will be able to lock on and continuously lock on at that stage. So I would recommend that besides also trying to do this, try to code a gradual change in frequency as well, right? I'll leave that to you as an exercise. But what's important here is we have managed, and we can just plot our frequency again because simulation is completed. So frequency plot. And you see that the frequency has settled. So the frequency has settled first at 51 Hertz. After the event, it has begun trying to settle at 49 Hertz, right? It has begun trying to settle, and the event is then reversed, or rather the system has been restored and it goes back to 51 Hertz, in which case the PLL again goes and locks on to 51 Hertz. So we now have a working PLL that can not only settle to the system frequency and achieve a steady state, but can also respond to system events. And it's important to understand that this is a drastic system event. So we do expect this PLL to perform much better under a regular system event, which would be a gradual drift in frequency. So with this, I will end this lecture. In this, we've talked about how the PLL performs under dynamic cases. I will have one more lecture in which we'll talk about how the PLL performs when the grid is not sinusoidal. So, as always, if you need any help, if you didn't get these results, you got any other result, or even better still, if you are trying something else out, please do post in the Q&A forum and I'll be happy to help you out. Otherwise, I will see you in the next lecture. Thank you so much and see you soon. Goodbye for now.